Okay, question 11. Which statement is correct about the forces acting on the object as the angle theta is increased? Okay, so we've got tension in the string. We've got the normal reaction force, which we draw normal to the surface. Okay, and the other force that we've got is the weight. There we go. So, let's just complete this diagram like this. Okay, there's a right angle triangle. That's theta there, that's theta there. So this one over here is going to be W sine theta. This one over here is going to be W cos theta. Alright, so let's take a look. The tension in the string remains constant. That's clearly false, okay, because the tension in the string is along is parallel to the slope, and that's balanced by W sine theta, sorry. Okay, so parallel to the slope, parallel to the slope, we've got W sine theta here, okay, and we've got the tension here. So as the angle increases, W sine theta is going to increase, which means that the tension is also going to increase, right? So it can't be A. The weight decreases. Nope. The weight of the block is only determined by the mass of the block and the planet that it's on. Okay, not the angle of the ramp, so that one can't be true. The weight component parallel to the slope remains constant. Nope. Okay, we've just talked that one through. That one can't be true. And then the normal force decreases. Okay, so the normal force is given by W cos theta. As theta gets larger, cos theta decreases, so W cos theta will decrease. Okay, and that's the force that's balanced. That's the force that's balanced out by the normal reaction force. So as W cos theta decreases, then that means that the normal reaction force will also decrease. Okay, so it must be B. So, question 12, there's the quick way of doing it and there's the long-winded way of doing it. Alright, I'm going to show you the quick way of thinking about it first, which is not mathematically rigorous, okay, but does get you to the right answer very quickly, okay, which is useful in a paper 1 situation where all you've got to do is get the right answer. Okay, let's give that one a go, but you've got to be really conscious that if you're asked to do this as a paper 2 question, okay, then the method that I'm just about to talk you through now, like, wouldn't hold water, right? So you would have to, you'd have to do it the long-handed way, which I'll also show you in a minute, right? Okay, so the idea is that the sigma F equals ma, and then we've got to think about, okay, what mass is getting accelerated, right? Well, the m2 is getting accelerated down, m1 is getting accelerated up. Okay, so it's actually both of the masses that are going to get accelerated, right? So that's m1 plus m2. Okay, both of those masses get accelerated. Where's that force coming from to accelerate both those masses, right? Well, we know that m2 accelerates downwards, so that means if this one's accelerating downwards, this must be the larger of the two masses, right? So the accelerating force comes from the difference of the masses, so m2 minus m1, all right, times by G, like that, right? And then we've got to find M1 over M2. So we're going to need to do a little bit of math there. What's the best way to do it? It's you divide G by A. Okay, so let's divide G by A. So then we get, on this side, we get M1 plus M2 over M1 minus M2, like that. But we also know that it accelerates downwards at G over 2, right? So then we can substitute that in. So now we've got G divided by G over 2, right? So the G's cancel, and that's 1 over 1 over 2. Okay, so that's just equal to 2. All right. M1 plus M2. Okay. Divided by M1 minus M2. Then you've got to multiply it out. So on this side, you're going to get 2 M1 minus 2 equals M1 plus M2. And then you've got to add M2, 2M2 to both sides, and subtract M1 from that side, so you end up with M1 over here equals 3M2 over here. Okay, and then you've got to do did I make a mistake somewhere there? Oh yeah, I did. Oh damn, that should have been M2 all along. It's M2 minus M1, my bad. Okay, why? Because M2 is the larger of the two masses. So we've got all of this the wrong way around. So it's minus like that. There we go. So actually M2 is equal to 3 times by M1. My mistake. So if you do M1 over M2 on this side, okay, then you've got to do 1 over 3 on that side. So there we go. We've got the answer as A. And that's the short way of doing it. Okay. The long way of doing it is actually, treating each of these bodies separately. So if you think about M1 over here, okay, then what's accelerating M1? It's the tension upwards. Well, it's the resultant force, right? Which is, so the resultant force that's accelerating it, so M1A, is equal to the tension minus M1G, like that. Okay? And then we can do exactly the same for this side over here as well. So we've got M2A. Okay, but now the tension's bigger, so it's going to be M2G. Sorry, now the weight's bigger than the tension, so it's going to be M2G minus T. All right, and then you're going to rearrange for T. So I'm going to call this equation 1 and equation 2. Okay, rearrange for T, so M2A minus M2G, like that. And then I'm going to take this equation and sub it into here. So I end up M1A equals M2A minus M2G minus M1G, like that. Okay, and if I rearrange that, then mistake again. M2. Yeah, of course I have. Oh my goodness. I'm having a bit of a nightmare here, aren't I? Yeah, I made a mistake when I was rearranging this, right? Okay, that should actually be minus there and a plus there. Goodness me. Don't let me near algebra today. So that should that should be a plus there. And that should be a minus there. Right. So then, when you do all of that, move all of the A terms with A in over to one side, and you'll get M1 plus M2. All right, and that's equal to all the G's on one side, so that's G, and that's M2 minus M1, like that. And then hopefully you can see that that is exactly the same as this equation here. And okay, I already did all of that algebra. I made a mistake in that as well, but I did get to the right answer eventually. Phew, thank goodness for that. So there you go. You got a question 12 was a bit of a dog. You should be rinsing through that in about 2 minutes. Like on average, these multiple choice questions should be taking you about 2 minutes. So, and if all that's a bit too much for you, right, you can totally get rid of 2 of the answers just by using your brain, okay, because for it to be a number larger than 1, all right, then that means that M2 would have to be smaller than M1. Okay, but we know that that can't be true because M2 is the one that's accelerating down, right? So we can straight away, we can get rid of these 2 answers, all right? And then flip a coin. All right, object suspended from a spring balance when the object's in air, spring balance, completely submerged in water, the density of water, blah, 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 blah. Right, okay, so let's draw out what's going on. When it's in air, we know that it's got a weight of 900 newtons. Okay, and when we submerge it in water, the spring balance now reads, okay, so in air, the spring balance would read 900 newtons, right? But now that we put it in water, it only reads 400 newtons. So how do we make the forces balance? There must be another force on here, okay, which is the buoyant force of upthrust, and that buoyant force must be 500 newtons, right? Okay, we've got the formula for buoyant force, which is in the data booklet. It is rho times V times G. Okay, and we know that that's 500. It gives us the density as 1,000. All right, V is the thing that we're trying to find. That's 10 over there, right? Can't do that in my head. Yeah, I think I can do that in my. I should be able to do that in my head, right? So that's 1 over 20. Okay, which is 0.05 meters cubed. Awesome. Answer B. More buoyancy joy. Right. Density. What is the density of the body? Okay. So, for this one, the weight is balanced by the buoyant force. So there we go. Weight downwards is balanced by the buoyant force. So we've got the equation for buoyant force. We used it in the last question, so that's rho times V times G. Okay. And the kind of key thing for us to get our heads around here is that it's the volume of the water that's been displaced, right? Okay, so it's not the volume of the entire block, it's the volume of the bit of the block of the water that's been displaced, right? Okay, so this is the density of water. Okay, and we know that because of the depth that it's floating in the water, we know that 3/4 of the entire volume of the block has been displaced, right? And what do we do next? Right, so that's the buoyant force, and we're going to equate that to the weight, which is the mass of the block over G. The mass of the block over G. Okay, and if we look at this, we can see that the G's will just cancel straight away. All right. So now we've got the density of water. That's by 3/4. And then this is the mass of the block. Maybe I should put block on there. Okay, and that's 3/4 of the volume of the block, right? So then if we move that over to one side, we've got the mass of the block divided by the volume of the block, which is, of course, the density of the block. Whoops. Which is the density. I'm calling it a block, they're calling it a body. You can use a subscript B for both of them, right? So the density of the body is the density of water, which they've just given us rho, 3/4 of that. There we go. Which one was that? D. 2 more to go. Come on. Right, resistive force that acts on an object moving through a fluid at speed v is given by kV. What are the units of K, right? Okay, so this has got to be homogeneous with respect to its units. So we're going to substitute in that's units of force in newtons. Okay, units of K are unknown, so we can just leave that as K for the moment. Okay, V meters per second, like that. Okay, and then we also know that force is equal to mass times acceleration. Units of mass are kilograms, meters per second squared for acceleration. So what do we got? Okay, we're going to do kilogram meters per second squared, and then I'm going to move all of the stuff over from the right hand side, so that's per meter, okay, second. Okay, and all of that's going to be the units of K. So units of K are kilograms, the meters and the meters disappear. Okay, seconds to the minus 2 times 5 seconds, that's seconds to the minus 1. Gets us D. Great, that was less than 2 minutes. We're speeding up a bit now, aren't we? 16, last one, here we go. So we've got the weight of the block, okay, downwards, and because it's on a flat surface, that's going to give us the normal, that's going to be balanced by the normal reaction force upwards, right? Okay, weight of the block is just mg, alright. What else do we need? Object is 2 kilograms, so the put force of 12. Right, okay. So we know that from sigma F equals ma. We know that for a mass of 2 kilograms, if it accelerates at 2 meters per second squared, that there must be a resultant force on it of 4 newtons, right? Okay, but if we're pulling it with a force of 12 newtons, okay, then that must mean that the pulling force minus the frictional force, okay, it gives us 4, so that's 4 there, that's 12 there, minus the frictional force. Okay, so that means that the frictional force must be 8 newtons. We're getting there. Okay, and then we look at for dynamic friction. Okay, that's the coefficient of dynamic friction. the formula that we need is FF equals mu D times by N. Okay, and we know that that's balanced by the normal reaction force is balanced by the weight. So instead of that, we can write mu D mg. Okay, and then over on this side, we've got 8 newtons. Mu D is the thing that we're trying to find, times by 2 kilograms times by 10. So we've got 8 divided by 20, which gets you 0.4. Job done. Over to paper 2 style questions next. I'm going to leave that one to Miss Hyman, I think.